And I don't see Mark and Sarah, but I would like to thank Mark and Sarah and the entire staff here at the Adler for hosting us here today. As Sarah mentioned, I've been with NASA at the Johnson Space Center for the past 30 years, but I grew up not 15 miles away from here in a suburb called Lombard, Illinois. And one of the reasons I'm standing here today is because when I was not much bigger than these youngsters here in the front row, I came here to Adler and I was inspired by what I saw here. So it's really great to be able to come back. So thank you for hosting us here today. We're going to start with a video that talks a little bit about exploration.
Hi, I'm Michelle Nichols. Years ago, I told you about NASA's new idea for a spaceship called the Space Shuttle. It was an exciting time, and we showed what we can accomplish in low Earth orbit. During the shuttle era, we built the International Space Station. Astronauts orbit the Earth conducting scientific research in space for the benefit of all humankind. And now, there's Orion, NASA's newest space vehicle, rocketed off the Earth by NASA's Space Launch System. The Orion spacecraft will be able to take us deeper into the solar system than we have ever gone before. So once again, we're about to begin a whole new era of exploration with endless possibilities where we can only go. Discover more about NASA's new path into the final frontier right here at this website. Orion, I'm on board.
I hope you recognized her. That was Lieutenant Uhura from the Star Trek series, another one of my inspirations. But as Michelle just told you, let me start off. From the years 1968 through 1972, a total of 27 Americans orbited the moon. And the moon, as you can see from this chart, is about 200,000 miles away from the Earth. Since 1972, every human spaceflight endeavor, ours, the Russians, the Europeans, has been confined to low Earth orbit. And everything that Rex just talked about, as fantastic as it was and as incredible as it continues to be, it's confined to this 220 miles right around the surface of the Earth. So what we're trying to do is we are trying to return humans to exploration, to return to visiting places beyond our home planet. And these are some of the destinations here. Orion is built to go to the moon, back to this 200,000 miles. We're built such that we can visit asteroids. Asteroids can be as far away as 3 million miles away from the Earth. And ultimately, our goal is to visit Mars, 35 million miles away from the Earth. So that's what this new NASA program is about. It's about exploring space. We're going to talk today. Rex showed you the result of essentially 40 years of space shuttle operations. Where we are in Orion, we are where the shuttle was in the mid-1970s when we were developing the vehicle. And I'm going to show you what it takes to build a vehicle today. Orion consists of basically three spacecraft subsystems. First, we have a launch abort system. And I'm going to show you what it takes to develop each of these in just a little bit. But at the far right is the launch abort system. This is something we never had on the space shuttle. We used to have it in the Apollo days. And what if there's ever a problem with the launch vehicle? That launch abort system allows the crew to be pulled safely away from the accident that is occurring underneath them. And you'll see in the videos we'll show in a bit, but that takes quite a bit of energy. That launch abort system, if we have to use it, works for a total of 2 seconds. And in those 2 seconds, it consumes the amount of energy that it would take to power 13,000 homes for a day here on Earth. The crew lives and works in something we call the crew module. And we can hold on exploration missions up to four crew. For low Earth orbit missions, we can hold up to 6 crew, but that crew module is designed, since these are longer term missions, to operate for up to 600 days. And Rex told you a little bit about what it took to come home in the fireball of the space shuttle. when you explore, you have to add velocity, additional velocity. So you can see, Rex said on the space shuttle, a typical reentry velocity is 17,000 miles per hour. When we come back from an exploration mission, we'll be traveling 27,000 miles per hour, which means our heat shield will get up to 6,000 degrees Fahrenheit, and that's the heat it has to dissipate. So that's a huge technology challenge. The last piece of Orion is the service module, and Rex talked a little bit about international collaboration. Human exploration is going to be the same thing. We've entered into a partnership with the European Space Agency, and the European Space Agency will be building the service module for us, and that's what will provide the electrical power and the propulsion capabilities for this flight. Rex also mentioned the Orion is a human spacecraft where the crew rides. It is the very top of this configuration, but to go on these exploration missions, we need a big rocket. That big rocket is called the Space Launch System. That's also under development at the Marshall Space Flight Center right now as we speak. And you can see a picture here of what it will look like when we meet up with that vehicle for the first time in the vehicle assembly building. This gives you some sense. This is the space shuttle that you just saw a great presentation on. It was about 184 feet when it was stacked. You can see the very first configuration of our SLS stack that we will fly on is 321 feet. And when we're done, when we have the heavy lift version, the 130 metric ton version, which is what we will use to go to Mars, you see how big that vehicle is. It will be the largest vehicle that we've ever built. This is our timeline. This is the history of the Orion program. We actually started in 2006. In 2010, we flew our very first test. It was a test of that launch abort system. And this year, 60 days from today, on December 4th, down at the Kennedy Space Center, we'll fly our first orbital test flight that we call Exploration Flight Test 1. And we'll be using a commercial rocket, a United Launch Vehicle rocket, to support us for that mission because the SLS is not quite ready yet. That rocket will be ready in 2017. Another unmanned test flight. We'll do one more test of our abort system in 2018, and then we will get back to human space flight, the kinds of things you just saw in 2021. I'm going to show you a little bit about what it takes to build a human spacecraft, but the reason it takes so long is because of those things that Rex talked about, the ascent, the reentry, having the systems work hundreds of thousands of miles away from the Earth. They have to be extremely reliable. A lot of work has to go in to make sure the spacecraft is ready to go. This is a depiction of what we're going to do in just 60 days from now. We will launch from Kennedy Space Center in Florida, and we will go around the Earth twice. On the second orbit, we will do an orbital raise maneuver. That United Launch Alliance rocket will raise what we call our apogee, our highest point in the orbit, to 3,500 nautical miles. That is the highest that any spacecraft designed for human beings has flown since the Apollo program back in the 70s. And then we'll come back after two revs. It's just a 2-orbit flight. It'll be about 4 hours long, and we'll land off about 230 miles off the west coast of the Baja, Mexico. And this is a short video that illustrates a test flight. Can you start that? This one does not have sound. I'll describe it. So we're on the launch, the ULA booster, lifting off from Launch Complex 37 in Florida. And one of the main objectives here is to show the mechanism deployment. And you'll see the mechanisms. These are fairings. Excuse me, that's the deployment of the Orion spacecraft from the core stage. Shortly after we do that, we jettison some fairings, and I'll show you what that's about in a little bit. And then here is that maneuver that sends us to 3,500 nautical miles. Really, the two main objectives of this test is to demonstrate all the key mechanisms and how they work. And then here you can see the crew module separating from the stack. And then to demonstrate the thermal protection system, the heat shield. That again has to withstand velocities about 50% larger than what we did in the shuttle program. Forward bay cover and 3 main parachutes. And you notice we land in the water, and we'll show you more about how we get out of the water at the end. So what does it take to build a spacecraft? And really, one of the reasons we're here in Chicago today, we have a large number of companies that supply parts to Orion are right here from the Chicagoland area. We're going to be visiting Rockford, Illinois. We're going to go to Indianapolis in a couple of days. But we're here to talk to the people that make components for the space shuttle. To make the Exploration Flight Test 1, there were a total of over 200,000 different parts that had to be logged into our factory at the Kennedy Space Center in Florida. And many of those started out in the lower right corner. You can see the green aluminum pressure vessel. This is the crew module pressure vessel. Inside is where human beings will live. But that started out as slabs of aluminum from Alcoa, from the Alcoa Aluminum Company. And then you can see they were machined because when you explore, when you leave Earth's orbit, every pound of mass is very, very precious. So we have to machine, we have a web pattern, and a lot of that machining takes place in companies right here in the Chicago area. The barrel, we call it the barrel, which is the big circular at the base of the crew module, was machined by Major Tool in Indianapolis. So all these parts go down to the Kennedy Space Center, and we erect what we call tooling. There are these white superstructures. We put the spacecraft in superstructures. This spacecraft, the green pressure vessel, arrived at the Kennedy Space Center in July of 2012, and we spend about 2 years attaching propulsion systems and batteries and computers and doing all sorts of tests. We'll show you some of the tests. And 2 years later, this is what the spacecraft looked in July of this year as we were finishing up the assembly. This is an example of one of the tests we do, and this test was conducted at the NASA's Langley Center in Virginia. Oh, we went too far, let's go back. There should be. We call this drop tests, and the reason we do drop tests is, believe it or not, one of the biggest loads that will hit the structure occurs when that structure hits the water. When we hit the water on a nominal day, we could be going 40 miles per hour. On a bad day, when the winds are blowing, and we also design the structure for a parachute failure, we could be going up to 65 miles per hour. So we do a lot of drop testing to make sure the structure can withstand the forces of landing. This is the second big subsystem of Orion. This is the service module at the Kennedy Space Center. And the service module here in the center is complete, and you can see on the tools on the left and right side of the picture, those are those fairings I told you. And the reason we designed fairings is because then we could make a very narrow spacecraft. We could save weight, and the load for ascent could be carried through the fairings. And on the way up, we can jettison the fairings so we don't have to carry the fairings all the way to the moon and back with us. Now, it's very important to make sure when we deploy the fairings that they actually work. So we did a number of tests. These tests were done in Sunnyvale, California. We did a total of 3. The first time we did the test didn't work. One of the fairings stuck. We had to make an engineering design change. And what you're going to see here is a video of the second test, and you'll be able to tell we were very happy when on the second test.
Video will cooperate.
Tried it.